Section 2.7 is related rates. So at this point, we've covered a handful of differentiation techniques like the product rule, quotient rule, and the chain rule. So we're able to take lots of different types of derivatives for functions of a single variable. In 2.6, we saw implicit differentiation, where we're able to take the derivative of, say, a variable y or some function of y actually with respect to x and correctly handle that situation, which typically means a factor of y prime or dy dx is generated when we do something like that. So all these tools are going to come together for this section of related rates. This is one of the harder sections that we'll do probably in the first few chapters of the course because they, for the most part, involve word problems. So here's some guidelines. They're not, always so helpful, but if you find, as you practice these problems, you find, you get to a harder type of problem, maybe going back and refreshing your mentality for how to work on these problems by reading this list might be helpful. And I believe the textbook also has some similar suggestions to this as well. So some of this is obvious and some is not. The first one's obvious, right? But don't take it for granted. Read the problem carefully and really understand what they're asking for and what they're telling you in the problem. Part two, this one's highlighted. It's going to stay highlighted because drawing a diagram is absolutely so helpful, right? Draw any diagram that could possibly help you with this. That's a good idea. At the very least, it's worth a little bit of partial credit. The third suggestion, or really step or strategy here, is to introduce notation. So, if it's something like a radius of a circle in our problem, then we could say the radius r, right? Let r represent the radius of this thing. Or if we're talking about the area of the circle, we'll say that the area capital A of the circle, that's an unknown quantity. Circumference c, right? Terms, variables that we're familiar with or that are suggestive are really powerful tools here. The next thing we need to do is express all the variables that are related together in some equation that will help us, right? So actually this is saying, before I get there, sorry, 4 is saying any variables that we know, write them down, right? So if we know a radius, right, r equals whatever the radius is at a certain instance, and then required rates in terms of derivatives, right? So if we know the rate of something, if we know that the radius is changing per unit of time, or that an area is changing per unit of time, or if a volume is changing per unit of time, we'll write something like dv dt, the rate of change of the volume per time step t, right? And that would be equal to whatever it is that they tell us if we know it. If we don't know it, it doesn't hurt to write something like d capital A dt, the derivative of the area with respect to time, equals, and then question mark. Just point out that we don't know what that is, and that might be one of the things that the problem's asking us for. So make a list of variables, write down the values you know, write down the things you might be looking for or that you don't know. Part 5 now says write an equation that relates the various quantities of the problem. So we don't have to make this up. We just have to remember how things are related. If our problem involves the legs of a right triangle, well, then we could write down a squared plus b squared equals c squared, right? And then we could have things like the derivative of a with respect to time, the derivative of b with respect to time, derivative of c with respect to time for the various legs. Some of those things may or may not be useful in the problem. Similarly, that could be done with x and y, and maybe this would be L or C or some number, right? But nonetheless, these equations that will show up will come from physical laws, right? The volume of a cone or the area of a circle, things like that. So one thing that geometry will do that we might want to consider when we look at the picture is keep our number of variables down to a minimum, right? Now, of course, put in the variables we need to know, but if we can use information in the problem to reduce 2 variables to just 1 variable because those 2 variables are related, well, that's going to simplify our work because those are fewer variables we'll have to take the derivative with respect to. So part 6, and this is also critical, right? Once you have a rate or an equation involving a rate or relation, sorry, I should just say a relation among the variables, we're going to ask about rates involved with each variable, right? We're going to see an example of this shortly. But in order to get there, we're going to need to use the chain rule, or really it's implicit differentiation. It's the same thing, right? Remember, implicit differentiation is basically the chain rule, right? ddt of a function of y, or ddx of a function of y for that matter, is whatever the outer derivative is, whatever's happening to y, right? And then times dy dx or dy dt, whatever the independent variable is, right? And that's just its implicit derivative with respect to that variable. So we're going to see a lot of ddt in these problems, right? We're going to take the derivative with respect to time because we're talking about rates most of the time. We're talking about how something changes over time, how a relation of variables changes over time. And then lastly, once we've taken this, done this oh so critical step, remember it's a calculus course, we should take a derivative somewhere when we're in the differentiation problems. So this is, if we're doing related rates, we're always going to need to take a derivative somewhere. Count on that. If you haven't taken a derivative, then you've either already written down a derivative you happen to know, or you're doing it wrong. So 7 is substitute the given information in the resulting equation and solve for the unknown rate. So we're almost always looking for some unknown rate while being given other information like fixed lengths or fixed values for constants, or a constant value for a parameter or a certain variable, and then we'll know a couple other rates or one other rate. We'll find the unknown rate. So we're almost always looking for a rate. So our first example keeps it pretty simple, and it splits up the work. This thing is split into two parts. Here's the first part of the question and then the second part. So this will let us demonstrate how we go about with those strategies from the previous page. Okay, so we're told if A is the area of a circle with radius r, so we're given the variables here, right? Maybe they said consider the area of a circle whose radius is blah, 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 right? And it expands as time passes, find dA dt in terms of dr dt, right? Or fine. So they've given us all these letters. We didn't have to do that work. I was trying to make it up without. But nonetheless, let's have at it, right? This is the most simple version of this, or one of the more simple versions we're going to see. So we're talking about a circle and its area, and the first thing we need to do is remember how a circle and its area are related. Well, there it is. In other words, what equation are they involved in? And it's this one. The area is equal to pi r squared, the radius squared. So then they ask, find dA dt in terms of dr dt. So in other words, find dA dt as a function of dr dt. All right. So the obvious thing to do is to take this equation here that we've already identified as being the relation between the two variables and take the derivative with respect to time on both sides. Well, on the left, that's just going to be dA dt, right? It's the implicit derivative of a with respect to time. This is technically not a very fancy function of a, right? It's a to the first power. Chain rule or power rule says 1 times a to the 0, so it's a 1 times dA dt is what the implicit differentiation tells us to do, and we get just dA dt here, where you just see it literally as that operator acting on that variable a. Now, on the right-hand side, pi is a constant, right? So don't forget, pi is really just a number. So it's some constant. So we factor it out with the constant factor rule, and we're taking the derivative of r squared now with respect to t. Do this as implicit differentiation tells us. 2 times r to the first power is the derivative of r squared, and then times dr dt, the implicit derivative of r with respect to t, right? R is some unknown function of t, so we have to write down its implicit derivative dr dt. Now that tells us dA dt, the rate of change of the area with respect to time, is equal to 2 pi r times dr dt. So not only does the rate of change of the area of a circle depend on the radius of the circle, but it also depends on the rate at which the radius of the circle is changing. Okay, so if we think about that, well, let's look at the next example and we'll see what's going on here then. So suppose oil spills from a ruptured container spreads in a circular pattern on the ground. So we're just assuming it's a perfectly circular pattern on the ground. Reasonable enough model. If the radius of the oil spill increases at a constant rate of 1 meter per second, how fast is the area of the spill increasing when the radius is 30 centimeters? Okay, so we're talking about a circular pattern on the ground of oil, right? And what we're being asked is how fast is the area changing, or how fast is the area of the spill increasing? So how fast is that circular spot of oil increasing in area? So what is the ADT? This is our question mark version of writing things down, right? It's good to identify the thing we're looking for as a symbol. Now, what's the information we know? We kind of poke through. We might not get this all in the same order every time, but the radius of the oil spill increases at a constant rate of 1 meter per second. We have 1 meter per second right here. This dr/dt. The radius changes at 1 meter per second. That's a rate. dr/dt is a rate of change of r with respect to time t. And then lastly, they give us another thing. They ask, what is the area, the rate of change of the area of the circle when the radius is at 30 centimeters, is equal to 30 centimeters. So we have 1 meter per second here. We have 30 centimeters here. Remember, to convert centimeters to meters, we just move the decimal place 2 to the left, right? In other words, 100 centimeters equals 1 meter. So we can make this conversion pretty quickly based on that in a stoichiometry table, perhaps. So now I'm ready to put all this information together. And luckily, the part above had us work on the relation that's involved here and come up with the related rates equation. This is a related rates equation right here. It's how these rates are related to each other. So now I have dA dt. It's 2 pi r, right? dr dt. This is all copied correctly from above. So I know some of this information. I know that r is 0.3 meters, so I'll plug that in for r. I know that dr dt is 1 meter per second. Plug that in for dr dt. With those two pieces of information, I now have everything I need in order to determine dA dt for this set of information, for this radius and this rate of change of the radius. So I have 2 pi times 0.3 meters times 1 meter per second squared. Now, a really nice thing we can do here is we can use unit analysis to make sure that our answer comes out, well, at least to error check it, right? Does this make sense? Well, I have 6 pi, so, or sorry, 0.6 pi. 2 times 0.3 is 0.6 times pi times 1 is really doesn't change it. Meters times meters per second, so I get meters squared per second. So my answer is 0.6 pi meters squared per second. Now, perhaps our homework online is going to want us to convert that to a decimal. That's pretty easy to do, 0.6 times pi in a calculator, and then you can round it to a suitable number of decimal places. Always do your rounding at the end of the problem, right? Carry pi along in its exact form until you get to the very last answer. That way everything is nice and exact, and then you can figure out what that is with the calculator as a decimal. Do our units check out? This is the rate of change of the area with respect to time. Does it make sense that it's measured in meters squared per second? Yeah, that's an area measurement per time measurement. So that works out just right, the rate of change of area per time. So it doesn't hurt. You don't always have to throw the units in, and you'll see me not do that in several examples and what follows. But it doesn't hurt if you've got the time to use that to check to make sure that your answer does absolutely make sense. And what it could do is it could help you realize that maybe you didn't do a good job here. Maybe you missed something here. So another thing that happens in these problems is the following, right? So one mistake that happens that you can check pretty quickly, like with the unit of measure or unit analysis, is not using all the information in the problem. So if you've gone through a related rates problem and you haven't used all the information they've given you, chances are you probably missed something like this derivative here, right? If we didn't use that 1 meter per second piece of information, we probably missed that, right? The unit analysis would catch it, but it could be another red flag for you if you realize, I didn't really know what to do with that information. I'm not getting this problem right. Should probably figure out how to incorporate that. So that's yet another thing to do. That's a common mistake, is to think you don't need all the information in a problem, and typically you do. We don't have many decoy many problems with decoy information, and then these problems are hard enough without that. So our second example. So this one's a little bit cleaner still, right? There's not really a word problem here, but they tell us to suppose y equals square root of 2x plus 1. So this is some half parabola. It's a root function, right? Where x and y are actually functions of t, some third variable. Okay. Then in part A, they ask us to find dx dt. Oh, sorry. They tell us that if dx dt is equal to 3, then find dy dt when x equals 4. So again, this is just more practice to set us up for the real thing and the main type of problem in this section. We didn't have to go looking for the relation this time. They gave it to us. They said these two variables, y and x, are related through this equation. And y and x also happen to be implicit functions of t, or just functions of t. To us, they're implicit because we don't know what they are. And they tell us, well, dx dt as a derivative of 3 is equal to 3, right? In other words, the derivative of x with respect to time t is 3. I just assume that t was time. Maybe it's not, but it doesn't hurt to think that in this case. Then they say find dy dt when x is equal to 4. So it must be that we're going to need all this information in order to find dy dt. So another common mistake that students will make is they'll get a relation pinned down, and sometimes there will be moments where we might use this piece of information in this relation for some reason or another, right? But not always. So don't jump to using that information unless you're absolutely certain that you need to plug this in here. If we were to just plug that 4 into this expression right here, well, then we haven't taken a derivative yet, so something's gone wrong there, right? And if we try to solve for y, well, we'll get some number, but we won't have used dx dt, right? We won't have used this important piece of information. And well, how are we going to get dy dt anyway? So what you want to do is once you write the relation down, and once you're sure of that relation each time, unless you're eliminating some variables because some variables are related in other ways. In this case, that's not happening. You really want to take the derivative of this with respect to t or whatever your independent variable is as soon as you have it written down. So you'll see throughout my examples that I have the relation, and once I do, pretty much the line right under that, I'll take the derivative, and I call that the related rates. It's how the rate of change of y is related to the rate of change of x. So again, ddt, derivative with respect to t of both sides. On the left, that's easy. It's just dy dt, right? The implicit derivative of y with respect to t. On the right, we have a little bit more work to do. We have a chain rule. 1/2 is going to come down as the constant multiple. The remaining powers to the negative 1/2. That's just using the power rule. The chain rule says to do that to the outer function and apply that to the inner function. And then multiply by the derivative of the inner function. Well, the derivative of 2x plus 1, well, that's just 2, right? In other words, here I've got the detail of that written here. The derivative of 2x plus 1 is 2. And that's with respect to time, right? We're doing that ddt of a function of x. So the last thing we need to do is, well, here's the derivative of this function that's not a function of t, but of x. So we need to multiply it by dx dt. Same reason we did that for dy dt back in section 2.6. So here are all our pieces, and this is cleaned up. 2 times 1/2 becomes a 1, and we've got this term to the negative 1/2 times dx dt. So here's our related rates equation. Now, if we know something like dy dt and x, or dx dt and x, or dy dt and dx dt, well, then we can solve for the other unknown. In this case, they give us dx dt is equal to 3, and they give us x equals 4. And they want to know what dy dt is. Find dy dt of s. So that's pretty straightforward. We plug in each of those numbers. We see that happening off to the side. And here it is, right? 2 times that x value of 4 plus 1 to the negative 1/2 times 3, which is dx dt's value. 8 and 1 is 9. 9 to the negative 1/2 is 1/3, right? All that's times 3, so 1/3 times 3 leaves us with 1. And there we have it. Dy dt is equal to 1 for that given set of information. Now note that, sure, this thing was a constant rate of change, right? dx dt. They just said it happens to be a constant rate of change. Typically, that's what's going to happen in these problems. We'll know that one variable has a constant rate of change with respect to the independent variable, which is most commonly t. But the other one we need to calculate. Well, the other one's not necessarily constant, right? Look at this function dy dt. Even though dx dt is a constant of 3, that's the case always, right? Because this thing's been given to us as that. It's not going to change ever. If we tried this at x equals 0, we'd get a completely different value, right? If x was 0, dy dt is going to have a different value. And we'd see that because x is 0 here. We have 1 to the negative 1/2. That's 1 times 3. When x is 0, dy dt looks like it's equal to 3, which is not the same answer we got here. Okay, so keep that in mind as well. We don't get to exploit this too easily to find the other rates in the problem because, well, the other rates, even though there are some constant rates, the other rates aren't necessarily constant themselves. They're a function of other variables potentially. So similarly, another question, if dy dt is equal to 5, find dx dt when x is 12. Okay, so now they tell us what dy dt is, and they say find dx dt for an x value of 12. So we've written down that whole the related rates equation. We've already done the work above, so we don't need to do much more here other than plug things in. Dy dt is 5, x is 12, and I just solve for this in the way that, or somewhat similar way, right? Only dx dt needs to be solved for as an algebraic variable, right? It's the term that we need to isolate. So we see that happening below. 2 times 12 is 24, plus 1 is 25 to the negative 1/2. So we flip it. It's 1 over 25. The 1/2 power is the square root. Square root of 1 over 25 is 1 over 5. And 5 is equal to 1/5 dx dt. Multiply both sides by 5, and we see that dx dt is 25. So that was just a follow-up. Now, it doesn't, for the problems that we'll see later, the more advanced versions of these that are coming up soon, they could ask one thing or another, right? They might be asking for dy dt if you know the other things, right? Or they might ask you about one of these rates. Typically, they're asking you about one of these rates that are blended in with the rest of these values, and you need to tease them out or solve for them algebraically. So that's yet one more step you need to sort of handle when you're dealing with these problems. But notice that so far, in each of these examples, we've always taken the derivative of both sides of an equation with respect to some third variable that's not necessarily in the equation, or we'll call it a third-party variable, right? It's not involved with anything there. It's essentially, most of the time it's t because we're talking about the rate of change over time. So this example, again, will fit that pattern just as well. So yes, it says, suppose a particle is moving along a hyperbola xy equals 8. So, or the hyperbola xy equals 8, right? As it reaches the point 4,2, the y-coordinate is decreasing at a rate of 3 centimeters per second. So now we're given that this rate of 3 centimeters per second. That's the y-coordinate. It's decreasing at a rate of 3 centimeters per second. We'll interpret that in a moment. How fast is the x-coordinate of the point changing at that instant? Okay, so maybe the very first thing I do when I see this is I say, okay, I've got a relation. They gave it to me. Something that's traveling along this path. So it's got some speed. So this is going to be a distance, rate of change in distance over rate of change in time. So I know I have ddt applied to both sides of this equation, right, or this relation. Okay. Maybe before I get there, just take some room. What's this thing look like? Is it actually a hyperbola? Well, yeah, y equals 8 over x. It's a rescaled version of y equals 1 over x, right? So, and I've labeled a couple points on this. There's this easy one, right? When x is equal to 1, it means that y was 8 and x was 1, right? 1 times 8 is equal to 8. So there we go. We have this point 1, 8. And then we have this other point 4, 2 that the problem claims is on the curve. And it doesn't hurt to make sure we understand everything well enough to see that, yes, 2 or 4 comma 2, the x value of 4, y value of 2, 4 times 2 is equal to 8. So sure, yeah, this is also on that curve. And that's really the point that we need. And now we can kind of imagine what's going on. This thing tells us that as it reaches the point 4,2, the y-coordinate is decreasing at a rate of 3 centimeters per second. So this thing is moving along, it's moving in the positive x direction, right? The negative y direction in order for it to follow that curve. Now, we don't really need to know that, but it's just good to know that, to understand it as we put it together, that's what the situation is. And we see that, yes, as y decreases, x will increase if we stay on this trajectory or on this curve. So here we have it, right? We have an x value and a y value, and then we have a rate of change for y, dy dt, and I put -3 here, and I'm being careful about that because they tell me that the y-coordinate is decreasing as it approaches 4,2. On the other hand, if they said the y-coordinate was increasing, I would know the motion would have to be this way. Again, I wouldn't have to do that. I wouldn't have to, because if I just write these pieces down as is, I'll get it right anyway. But decreasing rates are negative rates, increasing rates are positive rates. So keep that in mind when you work on these. So our relation xy equals 8 was given. We've graphed it. We've identified some pieces. We're not quite sure what to do about dy dt yet until we've taken a derivative of this. So I write the relation. The next thing I want to know, what are my related rates now? How do the rates of these things relate to each other? And that's found through implicitly differentiating the relation. So ddt of xy is equal to ddt of 8. Take the derivative with respect to time of both sides. Operations somewhat a lot like an algebraic operation. You do it to one side, you must do it to the other. And this is a product rule. The derivative of x with respect to time times y. That's the first derivative of the first times the second, plus the first times the derivative of the second. Right? So this is the derivative of y with respect to time, t, is that. So here we are, and the derivative of this constant is just 0. So there we have it. Now, what do we know? Well, we know that we're interested in the xy coordinate 4, 2, and we know that dy dt is -3. These pieces all just fit very nicely into this. I want to know dx dt. How is dx dt changing at this point? Okay, well, I know that x is 4, y is 2, and dy dt is -3. So there are those things, right? Now, once I simplify this and solve for dx dt, I end up with dx dt equals 6. It's just some simple algebra to isolate dx dt as a variable, right? As its own term. So, and that answer makes sense, right? When I look at this picture and think about this graph, if y is decreasing, my x values are increasing. So I should get a positive rate for x. So had I not done that, had I not put a -3 here, I'd have a +3. And this would make this a +12. And that would make this a -12. And that would make this a -6. Well, there's some conservation in that idea, right? What I would have said accidentally, and what I would have calculated accidentally as well, is that if they had this been +3, well, then I would be saying that, okay, if we're moving this direction along the curve, well, then x is decreasing at a rate of dx dt equals -6 at the point 4,2, while y is increasing at a rate of 3, +3 at the point 4,2. So note that there is that subtle difference. Okay, so that, again, still is not much of a word problem. That one's getting a little bit more into the weeds on stuff to challenge us some. But in the end, they still give us the relation. And if you just remember what a point is, x and y coordinate, and then identify this derivative, you're pretty much ready to go after taking the derivative of the relation and then plugging all the known values in and solving for any unknowns. Well, let's get into the real gist of these problems, right? Let's get into the actual applied scenarios. So this sounds like a classic word problem, right? We read this thing. It says, at noon, ship A is 150 kilometers west of ship B. Ship A is sailing east at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. How fast is the distance between the ships changing at 4 p.m.? Okay. Well, this type of scenario where we take two snapshots in time, right? The first one's at noon, the last one's at 4 p.m. What I like to do is draw this as two different frames, or as many different frames as there are relevant or explicit times. So at noon, ship A is 150 kilometers west of ship B. So I'll label my time frame here at noon and say, okay, here's ship A, here's ship B. Ship A is west of ship B, so it's on the left of it horizontally in terms of most maps, right? They're 150 kilometers apart. Okay, so that's about as good as I can do. Maybe I'll even say this, and I want to be really careful. I don't want to go messing my picture up too much by drawing my rates of change on there yet. So I'll just draw it down here. I'll say, okay, as a little vector, right? This little dot with an arrow, as a vector, right? I'm able to say, well, ship A is traveling east at 35 kilometers per hour, right? East is on to the right. This is north upward. East is to the right. West is to the left. South is downward, right? Okay. And then ship B is traveling north at 25 kilometers per hour. So in this moment, yes, they are exactly due east and west of each other. They're on the same line of latitude. However, this one's moving east, not changing that line of latitude that it's in, but B, and it's just a second later, is going to be off of that line of latitude. It's no longer going to be due east of ship A. But we freeze it right here just to set this part up. Now, this may or may not be very useful to us, but it will inform us as we move on. So at a later time, and what we want to be very careful of, I know I said 4 p.m. Maybe sometimes we would do that scenario, but at 4 p.m. we're going to be at a fixed location here and here, and we'll be able to determine that, right? And we'll talk about that in a moment. We're not worried about location, and that's the thing to get caught up in, is the actual position versus the rate of change. Okay, we don't really even know what we're looking for yet. So actually, let's come back around and say, what are we looking for? How fast is the distance between the ships changing at 4 p.m.? Okay. So that's a tough question, right? Because remember, at any time later, and this is why I've drawn this just arbitrarily. So for some time t, not necessarily 4 p.m., remember B is moving northward, right? So B is moved up here, A is moved eastward, and the distance between these two ships is now this straight line L. Well, the thing we need to realize is that this straight line L is the hypotenuse of a right triangle. Luckily, these two ships are moving horizontally to each other, right? They're one's moving east and the other north. Those are 90 degrees off from each other. So that's good. It's good to spot that. Probably our main relation that's going to be at work is going to be something involving the Pythagorean theorem, or sorry, the Pythagorean identity, right? That's the one leg squared plus the other leg squared equals the hypotenuse squared. Okay, now what are those values going to be? Let's see. Here's the thing. B is moved some distance vertically, we'll say, right, or northward. We'll call that y. That's usually the y-axis, the vertical one on the page. Now, A is moved horizontally, and this is the trickier scenario. We don't really know how far B has gone. It's just gone some distance y. We don't care. We don't want to fill that in yet, and that's tempting because you could say, well, it's traveled for 4 hours, noon to 4 p.m., and it's traveling at 25 kilometers per hour. Yes, that's the easy part. Don't go worrying about that right now. The hard part is to not let that information into this picture. This is an arbitrary time later. It's some arbitrary distance y. A has also traveled some arbitrary distance x towards B, right? Probably more eastward than B has traveled northward, but it doesn't really matter as long as we faithfully represent things on the picture. So A has traveled to the east by a distance x. What that means is that A has closed part of that distance of 150 meters, the total distance, or kilometers, the total distance, right? And they've done so by closing x kilometers of it, right? So what that means is this: if A has traveled a distance x, there's 150 minus x kilometers left between A's current position, and B's initial position. And why do we care so much about what that distance is? Well, it turns out that that distance makes up this leg of this right triangle. So if you see a right triangle start to appear in a problem, you want to pay close attention to it, and you want to write things down in such a way that you'll start to identify the components of the triangle that'll be helpful to you. And lastly, remember we called this L. Some point along the way, we might want to realize that, yeah, this is the length, this is the actual length between A and B. It's the hypotenuse of a right triangle. Now, again, we don't care what the length between the two is. They ask us how fast is this length changing. So let's see what we can do. So our relation, it's the important thing to get here, and it's one of the cruxes of this type of problem, is to get this relation correctly. Well, our relation is this length squared plus this length squared is equal to this length squared. And that's exactly what we see in that order right here. So that's good. We've got our relation written down. Unfortunately, sometimes one of these has to be a little bit messier than we prefer. Okay. However, this is just nothing but powers of variables. If we need to take the derivatives of these things, it'll be easy, right? Look at this. As soon as I wrote my relation, I've got my related rates equation that shows up. How are these? What are the rates of this relation, right? And that comes from taking the derivative with respect to time of both sides of this relation equation. And what we see is, by power rule, we have 2 times 150 minus x to the first power, right? 2 minus 1 is 1. And then the derivative of this inner function. That's the chain rule. Okay, we'll wrap that up in a moment in the next line. Plus 2 times y dy dt. That's a straight implicit derivative with respect to t, right? Of y squared with respect to t. And then same for L squared with respect to t. 2L times dl dt. It's power rule of that function of L, and then dl dt, because L and t are not the same variable, so they must be implicitly differentiated. Same thing for y and t. So how do we handle this? Well, just be careful, right? This is the derivative of this linear function, 150 minus x, and that just comes out to -1, right? So be careful with that. So the derivative of this function here is just -1. So that's -1. Oh, sorry, -1, and I should say dx dt, right? Take the derivative of x, a function of x, but with respect to t. So I need to put a dx dt there. Where'd the -1 go? So it's a little confusing. The -1 just got put out front, right? I could have put a negative dx dt here for this derivative, and then the next line down, put the minus sign out front. But there it is, once you've carefully done that. And what we're looking at now is our related rates. So now we could use this. If we know certain information later on in the day, or at any point in the day, then we can answer questions of anything they might ask. And in this case, what we do know is we know that ship A, remember, has a speed dx dt of 35 kilometers per hour. One thing I haven't quite done is make sure is everything in terms of kilometers. Yeah, all the information's in terms of kilometers, so we can move pretty happily without converting things. But be aware of that. That's one small thing that can come up. Ship B has a speed dy dt of 25 kilometers per hour. And so we can, write both of those things down. Potentially we could plug them in. Dx dt is 35, dy dt is 25. But what they're asking is, how fast is the distance between A and B changing at 4 o'clock? Well, we've got a little bit more to do here, right? And this part is just algebra. We're really done with calculus. We're not done with the calculus equation. That's this one, right? But we're done doing calculus. We've already taken the derivative. The rest of this is just trig, or maybe we call this algebra. Or sorry, the rest of this is trig and algebra. We want to know dl dt. That's the rate at which the length between them is changing at time t equals 4. Well, when t is equal to 4, we take our speed 35 kilometers per hour times 4 hours to get the x distance of 140 kilometers. So ship A has traveled 140 kilometers, all right, to the east. So it's gone 140 kilometers this way. So in other words, x is equal to 140 kilometers. That, again, is this little distance right here. Okay, and then y is the distance B has traveled. And if it's gone 25 kilometers per hour for 4 hours, it's gone 100 kilometers. Right? Quick conversion of time from velocities and lengths from velocity and known time. Okay, so what we want to know, so there's other pieces of information that we could plug in now, right? We could plug an x in here. We could plug that y value in here for the 4 o'clock p.m. time. The last thing we need to know, though, and we won't find dl dt because we don't know L. But how do we find L? And this is a common scenario, and this is where it gets confusing. This is finally where we get to go back and use our initial relation as though it's just an algebraic relation or a trigonometric relation, right? I know X, I know Y, I want to know what L is from this. And that's exactly what we can do right here. Here's X, this is 150 minus X plus Y is 100, right? Each of those are squared, and their sum is equal to L squared, right? That is nothing but our relation above from the Pythagorean identity, okay? Now, simplifying things on the left-hand side, we have 10 squared from this, which is 100, and we have 100 squared is 10,000. Add those two things up, and we'll get 10,100. And, well, L squared is equal to 10,100, so L is equal to the square root of 10,100. I don't take the negative of that because, well, that would be a negative length, and that really just wouldn't make any sense, right? Maybe it would mean that they're this side from each other. I don't know. We only need the positive version of that, so that's what we'll stick with for now. So if square roots come up and you solve for a length, just pick the positive one unless we have some sort of direction established or some position going on. So there's L. We know X, we know Y, we know dy dt, we know dx dt. So if I look at this, now I know all of these characters, and the only one I'm looking for is dl dt. So our final move here is to take this relation, once again, related rates equation, and write it down with all the known values in it. And here's what it looks like. 150 minus x equals 140 times dx dt is 35 plus 100, remember this is y, times dy dt is 25, is equal to the square, is equal to L, which is the square root of 10,100, times dl dt. So we need to simplify on the left and divide by the root 10,100. And this looks like this for dl dt. And then lastly, keeping my answer nice and exact, I end up with 2150 over square root of 10,100 kilometers per hour. I didn't put all the units in. I could have done that, right? We see that all these things should check out if we do that. Right, this would be meters times meters per, or kilometers times kilometers per hour. Everything's in kilometers times kilometers per hour. But once we divide by this length of kilometers, this kilometers per hour turns into, or kilometers squared per hour turns into kilometers per hour. So you can check the units if you like. That's a bit tedious and not informative in a problem like this, though. So, and of course, yeah, a calculator will handle the rest of this. Note that I don't do any rounding, right? I take this all the way to an exact form until I've solved for the thing I'm looking for. Then I'll plug this into a calculator. Then I'll submit my answer to an online homework checking app or whatever else is I might be working with. I'm on a test without a calculator. This is a suitable enough answer for me. So it might be a good idea, if you have a calculator handy, make sure this number is not insane, right? It shouldn't be 10 billion or shouldn't be negative something, right? It should be increasing. The distance should be increasing between those two ships. Yeah. Okay, so one more example, and this one's a bit tough as well. This involves a conical tank of water water leaking out of it, and water's being poured into it. And we know the dimensions of this thing. So let's just get to work reading it, right? So water's leaking from an inverted or out of an inverted conical tank. So in other words, the cone is pointing downward, right? The apex of the cone is down, an inverted conical tank, at a rate of 10,000 cubic centimeters per minute. Okay, so there's our first set of units, and we have a rate. So that's good to know. At the same time that water is being pumped into the tank at a constant rate. Okay, the tank has height 6 meters, so I'll immediately flag this. I have cubic centimeters, and I have a linear measurement of meters. So I don't really want that to give me too much of a headache. I'm going to convert those pretty early on. Now, next up, the diameter of the top is 4 meters. Okay, so let's take advantage of that. If the water level is rising at a rate of 20 centimeters per minute, when the height of the water is 2 meters, find the rate at which water is being pumped into the tank. This is definitely enough to make your head spin, right? But take it slowly, write down the things you know. First off, let's do some housekeeping with the units of measure. We have 20 centimeters per minute given to us here. I'm going to convert 20 centimeters per minute to meters per minute. Remember, 1 meter equals 100 centimeters. So 20 centimeters per minute is 0.2 meters per minute. Really, the game is just to move that decimal point 2 to the left. Easiest way to handle that. The other one might call for a stoichiometry table, right? I have 10,000 cubic centimeters per minute. I should write that as meters or cubic meters per minute. So I write 10,000 cubic centimeters per 1 minute. And in my stoichiometry table, I write my conversion factor over here. This is a form of 1, right? So 1 cubic meter is equal to 1 million cubic centimeters. Don't forget that fact, right? Do that carefully. Remember this. If 1 meter equals 100 centimeters, how do I get cubic meters? I cube both sides of this equation. And 100 cubed comes out to 1 million. So just, that's a little fact that could slip right by us. And then this is a form of 1, since these two things are equal, right? I multiply it so that cubic centimeters cancels, and I'm left with cubic meters per minute. And I've handled my units nicely, right? Got 1 over 100 cubic meters per minute, or I could write that as 0.01 cubic meters per minute. Okay, so that's maybe stalling, biding for time, but it gets you moving, right? It's a good idea to get moving, write down the things you know, and as you get that momentum together, you might be able to think through or roll it right into something that might have been more difficult for you in the problem. So the next thing I'll think to do is maybe draw a picture, right? I know this is an inverted cone, so I can draw an inverted conical tank. I know some facts about the tank. I know its height is 6 meters. I know its diameter is 4 meters. Then I know that at some point in this tank, the water level is going to be at a different height, right? So I'm going to call that H, because I know this is changing, right? This is, we're pumping water in, water's leaking out. This height is potentially changing thanks to that. And if the height is changing, if the water level is moving up and down, well, what we know about a cone is that this radius here is bigger than that radius there. So the rate or the radius is also going to change with the height. Okay, and then related to all of that is, of course, the volume, right? The higher up the cone the water is, the more volume of water there is in here. So we've got quite a few things to think about. Now, which of these things comes first to mind and which you label first is really, that's maybe a matter of personal style, but you might have thought of this first. You might have thought, okay, what's the volume of a circular cone, right? Well, that's volume V is equal to pi thirds R squared H. Maybe you thought of that, or maybe you looked it up on the internet. I'm going to need to know the volume of a cone in this one with radius R and height H. Okay, I find that relation and write that down. Probably pretty quickly, we'll probably write down that thing's derivative. But there's one other thing we have to prepare for, right? We've got water leaking in or being pumped in. We've got water leaking out. So Our leak, remember, is fixed, right? In other words, it's constant. We have 0.01 meters cubed per minute. Okay, so I can write that here. So out of here is 0.01 cubic meters per minute. Okay, so I know it's leaking water at this rate. We're also pumping water in. At what rate are we pumping water in? Well, that's actually the question. Find the rate at which water is being pumped into the tank. Okay, so I'm going to call that dPdt, and that's the rate of change of pump water per time, right? It's the amount of water that's being pumped in per time. It's not a very good use of a variable or conversion of a variable to a word. dV/dt would be better, but that's probably going to be taken by this. Okay. So, all right, let's try to put this together. dP/dt is the rate we're actually looking for. We know something about the volume of this conical tank, given any R and any H. Again, resist in the beginning any notion of putting in a 4 for R and a 6 for H here. That doesn't matter. Who cares what that is, right? The water level's not at that point, right? So, in fact, the only height we're interested in for the water level is this 2 meters. Don't plug that in yet either, but we'll use that later, right? So before we take the derivative of this thing, we really don't want to go putting too many numbers in here. Okay, one place where we can do that is in the following. However much water is being pumped into this thing, well, it's changing the volume of water that's in here. This amount right here is that volume of water that's in here. So it's changing the volume, and it's also changing the leak, right? So the rate at which water is being pumped in is equal to the rate at which the volume is changing plus the water that's leaking out. That makes sense, right? So if this thing is increasing in volume, the water level is increasing in volume, well, then it must be that we're pumping in water at a rate that's larger than the rate that water is leaking out. Okay, or vice versa. If dV/dt was negative and we're losing water in this thing, well, then we're pumping water in more slowly than it's leaking. Okay, but nonetheless, there's some conservation here. We know that the rate at which we're pumping water in is equal to the rate at which the water that's in there is changing in volume plus the amount that's leaking out. So the amount that's leaking out has now been handled. dP/dt is the thing that we're looking for overall. So we're really going to keep an eye on this. Now the missing piece to all this is dV/dt. And this is where the real work is hidden. Okay, so dV/dt, that's the volume of the water in the tank. It's given by this for a radius r and height h. So we can go down to the bottom here, and now we can finally do our related rates calculation, right? So we know if we take the derivative of this with respect to t, we're going to do that for both sides. We're going to have dV/dt on the left, and then we have pi thirds times d dt, this is a constant factor rule, of r squared h. So I've just slowly made a step out of this. I take the derivative with respect to time of both sides, and well, now this is a product rule, so I need to do 2r, the derivative of r squared, and then times dr dt, right? Dr dt is the implicit derivative of r with respect to t. It comes out of this calculation here. That's the derivative of the first function, then times the second function, h, right? This term here, h. And then plus r squared, it's this term, times the derivative of the second function with respect to time. Luckily, that one's a little easier. R squared times dh dt. So now we've got our related rates equation. And if we know dV/dt, then clearly we'll be able to find dP/dt. So now we have to get at it. For what settings do we need to know what dV/dt is? Well, what does the problem tell us that we haven't used is one clue. Well, the water rate is rising, or the water is rising at a rate of 20 centimeters per minute, or 0.2 meters per minute. It would be a good time now to identify this as dH dt. That's the rate of change at which the height of the water is changing. After we put this h in place, maybe we would have said that's dh dt up here. I'm doing it now because it's also a sensible time as well. So I know dh dt. Well, what else do we know? It's rising at a rate of 20 centimeters per minute when the height of the water in the tank is at 2 meters. So I know h is 2. Okay, have I written that anywhere? Not really, but maybe down here I'll say, okay, h is 2, right? And when I look at this related rates equation that I have, I need to know a lot of this stuff. I need to know r, dr dt, h, r squared, and well, r is r squared, and dh dt, right? I need to know r, dr dt, h, and dh dt. So far, I know h and dh dt. The problem gives me that. I need to exploit some more geometry in this problem. What I look at when I see this, what I see when I look at this inverted right circular cone is the following. There's really a right triangle here, right? With a leg equal to 6 here and 2 meters here, right? Half that diameter of 4 is 2. So this is a 2 and this is a 6. So I can use similar triangles to determine what this radius is in this arbitrary state by doing h over r is equal to 6 over 2. Right? Those are just similar triangles happening right there. So leg 1 over leg 2 equals leg 1 over leg 2, right, for the similar triangles. So corresponding legs. So h over r is 6 over 2. Again, just to see that. So there's our similar triangles move. And now h over r is 6 over 2, and that's equal to 3. Well, that tells me that h is equal to 3 times r. I multiplied both sides by r on this equation. So I have h is equal to 3r. Or in other words, I could solve for r. R is equal to 1/3 h. And that's great because I know what h is. And the problem says how fast is the, what we want to know is how fast is the volume changing when h is 2 and dh dt is 0.2, right? Well, h is 2, I can plug in h equals 2 here, and r is going to be 2/3 thanks to plugging that in. So r is 2/3, and now I know what to do here and here for my related rates equation. The last thing I need to know is dr dt. How will we go about finding dr dt? Okay, well, remember, I just wrote this down. I have another relation here. R is equal to 1/3 h. I know what dh dt is, so if I want to know dr dt, how about I take the derivative with respect to time of both sides of this? So ddt of this equation. So this is dr dt, that's equal to 1/3, constant multiple rule, dh dt, derivative of h with respect to t. Well, dh dt is 0.2, so I can plug in 0.2 right here, and then I'll be able to find dr dt. Well, 0.2 just happens to be 1/5, so I've done this as 1/3 times 0.2 or times 1/5, and that comes out to 1 over 15. So dr dt is 1 over 15. I now have all of these pieces. It took some work. I'm going to make some mistakes along the way. A problem like this is about as hard as it gets in this chapter or this section, and it takes a lot of practice to be able to do this well. You're going to have a lot of trial and error. You're going to get some things wrong. You're going to get stuck. But overall, you'll have to practice it until you're able to get through it. So let's put it all together. We have all this information, right? We're going to see this in the next page. This is going to be 1 over 15, r is 2/3, h is 2, r squared, we'll be squaring 2/3, and then dh dt is, I believe that's 0.2, yep, 0.2. And we put it all together, see what comes out of this thing on the next page. Really, we're at the sort of the finishing moves of this problem, the mopping up stage, right? So here are all those numbers plugged in. There's some arithmetic to simplify those. Looks like we're going to get a common denominator sort of accidentally. That's kind of nice. So we'll have 12 over 45 times pi over 3, All right, well, pi over 3 and then 12 in the numerator. 3 and 12 cancel to 1 and 4, respectively. So we'll have 4 pi over 45 is dv dt. Okay, so our rate of change of volume with respect to time is 4 pi over 45 for this specific moment, right? So for the given information regarding the height and the rate of change of the height. The very last thing we need to remember to do is this. We're not looking for the change in volume. We're looking for the rate at which water is being pumped in. Remember, we explained that the rate of change of the pump volume of water is equal to the rate of change of water in the tank plus the amount that's leaking out. So we just take this one value that we did all the work for, plug it in right here, and that's going to give us our meters cubed per minute value. So again, I didn't plug anything into a calculator here. I left it nice and exact. You could always go back and write it approximately as a decimal as needed, but it's best to leave things as exact as possible until you need an approximation. So that's a complicated problem. You might need to look through these notes a few times, working on it, trying it on your own. You definitely want to work up to problems like these. There are plenty of problems in the book. In fact, let's look at how many we have to do for the test. We have 1 through 27. So guaranteed the first third of these, maybe about 9 or 10, will be easier, straightforward. Basic problems like how we started. The middle will be maybe more like the ship. And then the last few, maybe the last third, as many as that, could be like the one we just did. It's complicated geometry with multiple scenarios of derivatives, right? We not only do we do the derivative of this relation, but at another point, we needed to find the derivative of this relation to be able to translate from one rate to another. So this is definitely a place where practice is necessary.